Hi, everyone. My name is Thomas Grunov. I am a postdoc at UMass in the group of Don Townsley, and I work on something called quantum information theory. Quantum information deals with applying quantum mechanics to things like computing, but also things like communication. I work primarily on the latter, but I also have some research that is applicable to computing. Well, why would one be interested in quantum computing or quantum communication? So it turns out you can do things that are impossible with quantum mechanics that are impossible sort of classical rule. And so that gives us extra power. We can perform certain algorithms or perform certain communication tasks that are impossible without quantum mechanics. One example is, for example, secure communication, but one can also look at certain algorithms that are way less efficient in the classical case. When I say classical here, I refer back to the non-quantum case. And I would like to give an introductory overview of quantum computing, also some applications of quantum communication, and this should be accessible for beginner computer science students. So let's get started. So maybe let's start off with the classical rule. Classical, so that's the non-quantum case. Well, our sort of fundamental unit there is the so-called bit. And a bit is either a 0 or a 1. Well, what does this mean? This means that maybe on a physical level, we might have some voltage that is low, that corresponds to 0, or we might have a 1, which corresponds to a relatively high voltage. And the fact that we have two distinct states means that we can encode information with this. Right, these sort of standard examples that we have Alice on one side, Bob on the other, and they agreed that if Alice sends a 0 to Bob, then they will not meet tomorrow at 1 p.m. And if she does send a 1, they will meet at 1 p.m. Right, so this is really how we can encode information. These zeros and ones are just really standard for anything else. And that allows these bits to represent and convey information. For computation, one can imagine that you may have some number which one can represent as a bit or a sequence of bits, and one can then input this into a computer that then runs some computation. So for example, if I have 2 bits, I can represent the numbers 0 up until 3, assuming we use 0 indexing. And so there's lots of things that we can encode with just classical bits. Really, all of computing and communication that we rely on, so your smartphones and your computer now, the thing that I'm recording is on, they're based on these classical bits. So they're already very useful. But it turns out that one can do better. One can look at so-called quantum bits, and they give you strictly more power. So what is a quantum bit? Well, it will be a bit hard for me to explain what a quantum bit really is. Instead, I will just try to give you some flavor of what it is, and I'll give you some hand-waving idea of what you can do with it. So we started with a classical bit. We could represent with either a 0 or a 1. In quantum mechanics, this is a bit more subtle. It turns out that if we want to describe a quantum bit, or shorter, a qubit, we represent it with a point on a sphere. So imagine this is a 3-dimensional sphere, and then the qubit is just a point, specific point on this sphere. It's maybe a bit hard to see, but you can imagine it as like your thumb pointing into a certain direction, And the direction that your thumb is pointing in encodes the state of the qubit. Okay, well, what does that mean? Well, on the physical level, one can think of this as something called the spin, for example, of an electron. This is just an example. And unfortunately, if you are not a physicist or have a physics background, this might not mean a lot to you. But it turns out that small particles, like, for example, electrons, they can have a property called spin. And for an electron, for a very specific reason, it turns out you can visualize it as the electron having a sort of arrow sticking out of it. This is a very, very simplified picture, but it still gets the message across and gives you most of the intuition that you're needing. And so you can think of this electron having an arrow sticking out of it, and this arrow can point into different directions. And in all the different directions encodes the different states of this electron. So it's a bit hard to see on this drawing here, but you should imagine this arrow here sticking out from the center of the sphere, pointing out to some point on the surface of the sphere. Okay, well, here you can already see very much the difference between a classical bit and a quantum bit. A quantum bit can sort of point in any direction. And so we have a sort of continuum, an infinite number of directions that we could point in, and potentially could also encode a lot of information. So let's see. So it seems that quantum gets its power from infinite number of states. Question mark. The question mark is important here. This would be a sort of naive interpretation of what I just said. And it turns out the truth is more interesting, but also more complicated. Yes, those two are related. And let me get into detail why that is. So indeed, the way I phrase it now, it might seem that this principle that the statement here that I just wrote down seems true. Like you could use this to encode a lot more information. You know, for example, if Alice wanted to send some floating point number, some number between 0 and 1, to Bob, she could just, in principle, choose to send her qubit across a specific direction and use that to indicate the number that she wants to send. Right? If you think of the angle that the qubit makes with, for example, so now I just view it from the side. If we think of the angle theta that the qubit makes with the horizontal axis, then Alice could choose any kind of angle that she wants and then send this to Bob, who could then check this angle. And then they could potentially encode an infinite number of bits just in the angle that is transmitted. But it turns out it's more sophisticated. So let me explain what I mean by that. So let's say I give you a qubit that is pointing up. Right? Think of the electron, arrow pointing up. And now we're going to send this qubit into a machine. It's called machine M. And this machine, what it is it's a measurement device. It's really a thing that you can set up in your lab. And what this measurement device does, it answers or asks the question, are you pointing up or down? And this measurement device will take in this qubit and then answer or ask this question and return an outcome. And so if you put in this qubit that's pointing up, put it through the machine, it will tell you, well, yes, it was pointing up. Okay, that's not too surprising. Well, what happens if we now ask the same question for down? Again, put it into the same machine. Well, not too surprisingly, we'll get down now. So you just take an electron, put it through the machine, and ask, are you pointing up or down? Well, we have more directions than just up and down with a qubit. So let's put in a qubit like this, pointing out to the right. But simultaneously, we're going to take our measurement device and sort of flip it. We're going to rotate it by 90 degrees. And we get a new measurement device, M prime. And now what this measurement device does, it asks the question, are you pointing left or right? Well, what will happen here? Well, again, not too surprisingly, the machine will say, well, you were pointing right. But now let's think of what happens when we input a qubit that's pointing up and put it back through our original machine, M, which asks, are you pointing, oh, sorry, my bad. Let's do pointing to the right here. And now the machine M asks, are you pointing up or down? What will happen then? Well, this seems like a bit of a silly question, right? The qubit is pointing to the right, and we're asking, are you pointing up or down? Now, even though this might sound like a silly question, it really gets to the heart of quantum mechanics. And it turns out that this measurement device M that we're making, it's not just some quirk of this machine that it can only ask this question up or down, but what quantum mechanics tells us is that we're really limited in what kind of measurement devices we can build. In a certain sense, every type of measurement that we perform needs to sort of abide by these weird rules that we can only ask these types of binary questions, like are you pointing up or down? More specifically, we can never ask a question, which direction are you pointing in? Quantum mechanics sort of precludes that for some bizarre reason. So what then? What will happen then if we ask the question, are you pointing up or down, when the qubit is actually pointing to the right? Well, in that case, we will get a random outcome. With 50%, we will get up, and with 50%, you'll get down. And more importantly, when we get this measurement outcome, it's not just the device that tells us, oh, you were pointing up. If we then look at the state afterwards, it will be as if it was pointing up all along. And if we got the measurement outcome down, we will see that, hey, the state was actually pointing down. So this is very weird, right? We have a state, which means the qubit is pointing into a certain direction. And we ask it a question, and first of all, we get a random outcome. And depending on the measurement outcome, our state will have changed. And so the measurement outcomes that we get here, they don't tell us anything about the state beforehand. And so we cannot really access the information of a state. We might get random outcomes, and we're not sure whether we reveal some actual information about the state that we looked at. And with this in mind, I want to go back to sort of this statement here. Right, we had this very naive idea that we could send maybe a qubit with a certain angle theta from Alice to Bob. Just to make it clear, this is a theta here, the angle with the horizontal axis. And we could potentially send this qubit from Alice to Bob, and then they could encode information in this angle. But even though this qubit does indeed possess sort of this property, it has an angle with the horizontal axis, it is information that Bob cannot access. Why is that? Well, he only has access to these measurement devices that ask questions like up or down, or maybe to the left or right. And in general, he can only ask questions like, are you pointing this direction or the opposite direction. So there's this very interesting trade-off that it seems like quantum mechanics gives us more power because now we have a continuum of states, these directions of a qubit that we could choose from, but we're somehow limited in the types of information that we can extract from it. And so quantum information theory is sort of this very nice art of trading these things off. And in a very certain precise sense, quantum computing will be all powerful. You could basically compute anything you would ever want to, ignoring some details, weren't it for this fact that we only have limited access to the underlying state. So if we could ask questions like, oh, which direction are you pointing at? Then quantum computing will be insanely powerful. But that's not the case. We are limited in types of questions that we can ask, and that also limits the power of quantum computing. Well, of course, quantum computers, QC, are still useful for something. And let me give a very silly example. Well, not a silly example, but it will seem silly at first. It can solve questions like this very fast. 15 equals 3 times 5. Well, this is not too surprising, but the idea is that this number that we have here on the left is a product of 3 prime numbers, 3 and 5. And if I give you such a number that is a product of 2 prime numbers, and I ask you to find those 2 prime numbers, well, in this case, you can still do that. You could still, often not too much hard work, you can find, hey, that's 3 times 5. But if I make this number very large, then it is hard, even for a classical computer. And the idea is that going sort of from the left to the right is hard for a classical computer, at least. But if I give you the 2 prime numbers here, it's very easy to go to this side. I just take the 2 numbers and multiply them. This is easy to do on a classical computer. So this is easy. Now, these types of problems where going in one direction is hard, but the other direction is easy, these problems turn out to be very useful for cryptography. You can think of this as a sort of lock. If you don't have the key, it's very hard to open the lock, but if you have the key, it should be easy to open up the lock. And we're skipping a lot of details. This is sort of really what a lot of current security systems are built on. So if you send messages over the internet using your phone or your computer, they all rely on something called RSA, named after the 3 inventors. And the thing is that for classical computers, we believe this is a hard problem. But if you have a quantum computer, there's a specific algorithm that you can run for which you can solve these types of problems, even for large numbers, efficiently. And so quantum computers would, for example, break a lot of the current encryption systems. That is one reason why you might care about quantum computers. If you're interested in physics or in chemistry, then quantum computers are also very useful for simulation. So the hand-waving idea is that if we want to simulate quantum systems, there's a sort of overhead if you want to simulate them with classical mechanics, or better said, classical bits. And it's way more natural to simulate quantum systems with, well, actual quantum systems. Well, why would you want to simulate quantum systems? Well, basically everything is already quantum. So if you're interested in, for example, understanding a molecule, which you might use for some type of medicine, or for building a new type of material, you would want to simulate it to see how it works before you spend a lot of effort trying to develop it. So quantum simulations has applications in medicine and material science. I will now quickly mention one application of quantum communication theory. Quantum communications. There's something called quantum key distribution, often shortened with QKD. And very hand-wavingly, the idea is that we can use this to send information, or to be able to securely send information between Alice and Bob. And I won't go into detail exactly how this works, but it relies on this idea that when we send a qubit across, maybe for example, Alice sends a qubit in this direction over to Bob, then they can check whether someone tampered with this qubit or tried to read off this qubit. I'm again skipping all the details, but the idea is that if there's some eavesdropper here that tries to put in some measurement device, well, this measurement device needs to ask, are you pointing up or down or this and that direction? And if the eavesdropper does not know the state or the direction that Alice is preparing the qubits in, this measurement device might alter the state, right? Maybe the measurement device is asking, are you pointing this direction or that direction? And after measuring, the eavesdropper does not know which state Alice has sent. And so by checking, sort of comparing the input states and output states, which I'm ignoring how you do that, you could check whether someone is trying to eavesdrop or trying to listen in on your conversation. Up until now, I've been mostly talking about just a single qubit. It turns out that things get a lot more complicated when you start looking at multiple qubits. I will sort of give a very brief sketch, and I'll fill that with a very brief sketch of how it looks like when you have multiple qubits. And to do that, I'll first compare this a bit with the classical case. So we saw that for a single bit, we had either a 0 or a 1. And I'm now representing this on a line or 2 points that are connected by a line, 0 and a 1. If I now take 2 bits, then I have possibility 0, 0, 0, 1, 1, 0, and 1, 1. And those I can conveniently describe as a square. And here's 0, 0, 0, 1, 1, 0, 1, 1. This representation is nice because I can think of these points, these bits, as really the location in a two-dimensional plane. This point here has coordinate 0, 0. This point here has coordinate 0, 1, 1, 0, 1, 1. So why stop there? Well, if we look at 3 bits, we can now get something similar, but we get a cube. And so this point would correspond to 0, 0, 0, this one to 1, 1, 1, 0, 0, 1, and I won't draw the rest. And in general, when we go up another dimension, we would get a 4-dimensional hypercube. And in general, if we have n bits, we get an n-dimensional hypercube. And the nice thing is that we can now sort of think about bits more geometrically. We can think of computation as sort of transformations on this hypercube. And it's sort of a geometrical picture that carries over to the quantum case as well. So I will have to lie a little bit, or at the very least, hand wave or ignore some details. But one can think of it as follows. For a single qubit, as I mentioned before, we have sort of the surface of a sphere. Well, the surface of a sphere is really a two-dimensional thing, right? If I'm standing on the Earth, there's sort of two directions that I can walk in. I'm assuming that I cannot just go up in the air. And so there's just two independent directions. So we call this a two-dimensional sphere. Now, if I go to 2 qubits, well, I already cannot draw that anymore. There's too many dimensions for that. But it turns out that in a certain sense, I can think of my qubits as having a 4-dimensional, as being the points on a 4-dimensional sphere. Or sorry, think of it as the points on a, well, like I said, I need to ignore some details. First of all, there's a complex here. This has to do with complex numbers, if you have seen those before. Well, let me ignore the sphere here for now. Or actually, no, let me add that. Yes, this is a little bit annoying to explain how exactly this works. But let's say in general, we can think of, if we have n qubits, we can think of some very high dimensional sphere. And it's a point on this sphere that describes the position or sort of the state of multiple qubits. And so we can see that already this sort of geometric picture still carries over to the quantum case. And just like how in classical computing, we could think of transformation of this hypercube as some form of computation, we can think of rotations of this higher dimensional sphere as the type of operations we would want to perform in quantum computing. Again, I'm skipping lots of details, but the idea is to just give you some flavor, some idea of what quantum computing is. So we're looking to do some projects, and the nice thing is that you don't need to understand what a hyperdimension or what a higher dimensional sphere looks like, or what a complex dimensional sphere looks like even, to do research in quantum computing and quantum communication theory. In the next couple of lectures, I want to talk about certain states, which means certain configurations of qubits. And these states, they will be highly entangled. And so in the next video, I would like to talk a little bit about entanglement. This is one of my main research interests. And I want to talk a little bit about a specific subset of states for which I'm very interested in understanding this entanglement. And these states are called graph states. The nice thing about these is that they require no to little background. On quantum mechanics. And so I would like to give an introduction and really start with it from a very high level, such that you can get some understanding and maybe start thinking about it yourself for possible research questions that might be interesting to look at.